Welcome to Brain Vision.
So let's draw a diagram of the system. We can have a horizontal axis here. And from this distance to here, this would be considered L over 2. From this distance to this distance, this is L over 2. Again, this is not drawn to scale. We have an angle here, theta, and we can say from this distance to this distance, this would be L over 2 times 1 minus cosine of theta. And we know that here, mechanical energy is going to be conserved. So this means that the total kinetic energy would be equal to the rotational energy. And this would equal 1/2 I omega squared. So we can say that E initial equals E final due to the conservation of mechanical energy in this case. Therefore, the initial potential energy would be equal to the final kinetic energy. So we can say mg 1/2 of L times 1 minus cosine of theta. So that would essentially be the height. And this would be for the gravitational potential energy. This would be equal to 1/2 times the moment of inertia times the angular velocity at the bottom squared. And we're going to use the moment of inertia for a rod rotating about one end. So the moment of inertia of a rod rotating about one end, this would be 1/3 ml squared, and then again times the omega squared, the angular velocity at the bottom. Therefore, the angular velocity at the bottom would be equal to the square root of 3g over L times 1 minus cosine of theta. And the linear velocity at the bottom would simply be equal to the angular velocity at the bottom times the length of L. Therefore, the linear velocity at the bottom would be equal to the square root of 3gl 1 minus cosine of theta. So this would be the formula for the linear velocity and the formula for the angular velocity. That is the end of the solution. Thank you for watching.